Welcome to the all ions, which is an example of Qual-Quant integration. Now, the purpose behind all ions is to use Quant for the determinations and get conformational evidence from the fragment ions. Now, the work is done by Qual, and you can see here in Qual we have the coevolution curves and their profiles, and you can do that discovery end, which I'll go over very quickly here, to find the target ion and the spectrum of the fragment ions. Here's the workflow that we're talking about, basically flipping back and forth between high and low, either fragment voltage or with a QTOF, the collision energy in the collision energy cell, producing alternate scans so that you can see the MS1 of the low energy as well as the MS1 of the high energy. And that discovery part is done in Qual, then transferred into Quant, and what I'll show you is the quantitation part. Let's take a look at the quantitation flow chart. And as you can see here, we're going to do target analysis with the target ion. That's the strong molecular ion, attic species. And then we're going to go after the qualifiers to produce conformational evidence. And as you can see, we're going to do extraction and look at those from a chromatographic viewpoint, studying their qualifier ratios in the traditional quantitation sense, getting a final concentration and the qualifier ratios of the fragment ions that come from the high to give us more information. Let's take a look at the Quant method editor to understand the setup for the target and qualifiers. So we'll study a compound nitrazepam, and here's the target, which has a fragmentor of 110. Now, we're also going to pick up for the first qualifier the isotope of that. There's about a 1 unit mass separation here, and that also shares the fragmentor of 110. So the fragmentor voltage here from the MS scan shows the molecular ion plus a predominant isotope in Quant. So let's further study the qualifier fragment setup for the fragment ions from the high collision energy. And you can see here, here's the collision energy of 20 and 40, and these ions are fragmented. They're at a lower mass than the original molecule, and the fragment ion conformation shows these accurate mass fragments generated from the collision energy, which are specific for the molecular 3D structure, which determines how that molecule fragments given that amount of energy. All right, let's start this up from scratch for the demo, and I'm going to create a new batch, which I'll call all ions, and then I'll add the samples. And next, the important step, I'm going to read in the information from Qual, which is stored in the form of what is called a chef file. So there's the chef file that I've created from Qual, and I'll read that in and look at it in the method editor. So let's concentrate on nitrazepam, and as you can see from the default method, I've created a target, and here for my first qualifier, I've taken one of the isotopes, and the second and third qualifier come from the higher collision energies. So next, let's do a couple additional things like set up a calibration table. So I'm going to add in 3 levels, levels 1, 2, and 3, with some concentrations. And I'll copy those to the other compounds. And now I'm ready to apply and see what that looks like in batch at a glance. So let's zoom in with fit to peak and observe the target here, which gives me my final concentration, as well as the qualifier ratios as they're overlaid here in normalized format. And I can zoom through my compounds and then decide, looking at them, whether they fit the behavior that I'm expecting, and then make that determination with confidence. Last, let me mention the default behavior. There is an XML configuration file which offers the possibility of altering the behavior. By the way, the demo that was recorded was with the max number of qualifiers generated from the precursor ion, as pointed out, the precursor ion at the low energy is set at 1. The default behavior as seen here is 0. So all the qualifiers are generated from fragment ions. Thanks for your attention.